Hello students, welcome. Today, lesson 41, form 3, topic 3. We want to proceed to combining volumes of gases. So we're saying this section deals with the combining volumes of gases when they react at the same temperature and pressure. For calculations involving gases, volumes are preferred because the volumes are easier to measure than the masses. So we're saying the relationship between reacting volumes of gases is summarized by Lusac's law. So let us see what Lusac's law states. So we're saying Lusac's law states that when gases react, they do so in volumes that pair a symbol ratio to one another and to the volume of the product if gaseous, temperature and pressure remains constant or remaining constant. So during the exam, you can be told state the Lusac's law. So we're saying it states that when gases react, they do so in volume that pair a symbol ratio to one another and to the volume of the product if gaseous, temperature and pressure remains or remaining constant. So next, let us see Avogadro's law states that equal volumes of gases will contain equal number of particles. So let's see next problems involving Lusac's law. Example 1. So example 1, we are told 150 centimeter cube of nitrogen gas was reacted with 330 centimeter cube of hydrogen gas. So part A of the question, we are told write the balanced equation for the reaction. So here we have nitrogen gas. Let's write nitrogen gas reacting with hydrogen gas. So when nitrogen reacts with hydrogen gas, we are going to get ammonia gas. So NH3 is the formula for ammonia gas. So next, let's balance the equation. We have to put 3 here and we have to put 2 here to balance the equation. So we go. Part B, we are told assuming the reaction went into completion and that all the volumes were measured at the same temperature and pressure. So we are asked to calculate Roman 1, the volume of ammonia formed. The volume of ammonia formed. So here we are given the volume of nitrogen gas to be 150 and the one for hydrogen gas to be 330 centimeter cube. But if you check the mole ratio, it is 1:3:2. So that means nitrogen and hydrogen, one of them was in excess. So the one that was in excess is nitrogen gas. Because when you check the mole ratio for nitrogen to hydrogen is 1:3. So if 150 is multiplied by 3, that will be 450 of hydrogen gas. But we don't have 450 of hydrogen gas. We are given only 320. So that means the volume of nitrogen there was 110. So that when it's multiplied by 3, it gives us 330 centimeter cube of hydrogen gas. So here we have seen that nitrogen was the one that was in excess. So when we are dealing with the comparing the ratio, we are going to use for the formation of ammonia gas, we have to use the ratio between hydrogen and also ammonia gas. So we are going to say hydrogen ratio ammonia gas is 3:2. We know the volume of hydrogen gas, which is 330. So we can ask ourselves, what about the one for ammonia gas? We cross multiply. There, we are going to say 330 multiplied by 2, then divided by 3. Here, we are going to get 220 centimeter cube of ammonia gas. That will be the volume of ammonia gas formed. So we proceed to Roman 2. So in Roman 2, we are told total volume of the gaseous mixture at the end of the reaction. So if you remember, we said nitrogen was in excess. So first of all, we have to see the volume of nitrogen gas. So volume of nitrogen will be equal to 330 divided by 3. This will be 110 centimeter cube. So let's say again volume of the unreacted nitrogen, the unreacted nitrogen. This will be equal to the 150 given in the question minus the reacted volume of nitrogen gas, which was 110. Here we are going to get 40 centimeter cube of unreacted nitrogen gas. So next we are going to get, we are told total volume of the gaseous mixture at the end of the reaction. So we have 40 centimeter cube of nitrogen gas, 40 centimeter cube of nitrogen gas, plus the 220 centimeter cube of ammonia gas. Remember, ammonia gas was product. So here we're asked the end of the reaction. So we are going to add plus 220 centimeter cube of ammonia gas. So when we add this, we are going to get 260 centimeter cube as the total volume of the gaseous mixture at the end of the reaction. So we're done question 1. So in question 2, we are told 250 centimeter cube. So in question 2, we are told 250 centimeter cube of methane was burnt in 600 centimeter cube of oxygen at room temperature and pressure. So calculate the volume of the residual gas. So here, first of all, we have to write the reaction between methane and oxygen. How do we write methane? Methane is written CH4, methane gas plus oxygen gas. Here we are going to get carbon dioxide gas and also water, liquid. So next we have to balance the question. When we are balancing, we put 2 here and we also put 2 here to balance the question. Okay, so if you have that, let's see the mole ratio between ammonia ratio oxygen, it's 1:2. The one for carbon dioxide, it will be here also 1, with the water, which is 2. So we are given 250 centimeter cube of methane gas, which was burnt in 600 centimeter cube of oxygen. So when we check the mole ratio between methane and oxygen is 1:2. That means one of these is in excess. Let's check the one that's in excess. So if we have 250 for methane, the volume of oxygen will be times 2 of this, which is 500. But here we have 600. That means it is oxygen which is in excess. Okay, we're asked to calculate the volume of the residual gas. So let's get volume of oxygen. Volume of oxygen reacted or used. Here will be 250 multiplied by 2. So here we are going to have 500 centimeter cube. So next let's get volume of the unreacted oxygen. This one we are going to say 600, which is given, minus the 500 that has reacted. Here we are going to get 100 centimeter cube of unreacted oxygen gas. So next, in the product side, we have carbon dioxide being gas or being gaseous product. So the mole ratio between methane is equal to the one for carbon dioxide. So mole ratio between methane ratio carbon dioxide is 1:2, is 1:1. So that means volume of carbon dioxide formed is equal to 250 centimeter cube. So we are told to calculate the volume of the residual gas. So we can say the residual gas is 100 centimeter cube of oxygen gas, and we're having 250 centimeter cube of carbon dioxide gas, or we can say 100 plus 250, this will be 350 centimeter cube of residual gas. That's how we can answer for that question. We got question for question 3, we are told determine the volume of oxygen will be required to burn hydrogen produced when excess zinc granules react with 200 centimeter cube of 0.5 molar hydrochloric acid at room temperature and pressure. Okay, we can start by looking moles of hydrochloric acid. How do we get moles of hydrochloric acid? Molarity, which is given 0.5, multiplied by volume used, which is 200, divided by 1000.
There's no internet connection at the moment.
So we are going to get 0.1 moles. So next, let's write the reaction between zinc and hydrochloric acid. So we are going to have zinc solid plus 2 moles of hydrochloric acid aqueous. We are going to get zinc chloride solution plus hydrogen gas. So here we can get the number of moles of hydrogen gas using the mole ratio. So hydrochloric acid ratio hydrogen gas is 2:1. So we have the number of moles of hydrochloric acid to be 0.1. So we can ask ourselves, what is the number of moles of hydrogen gas? 0.1 multiplied by 1 divided by 2. Here we are going to get 0.05 moles of hydrogen gas. That will be the number of moles of hydrogen gas. So next, let's get the volume of hydrogen gas at RTB, because we are told at room temperature and pressure. So we can say 1 mole of hydrogen gas produces 24 decimeter cube at RTB. So we can ask ourselves, what about 0.05 moles of hydrogen gas? What volume can it produce? So we can cross multiply. We can say 0.05 multiplied by 24 divided by 1. So what are we going to have there? So we are going to get 1.2 decimeter cube of hydrogen gas. So next, let's proceed. So in the next step, let's check the demand of the question. What the question is asking, we are told determine the volume of oxygen will be required to burn hydrogen. So if we get the volume of hydrogen in decimeter cube, let's write the reaction between oxygen and hydrogen. So hydrogen gas reacts with oxygen gas to produce water, which is liquid, or steam, which is gas. So to balance the question, we have to put 2 in the side of water and 2 in the side of hydrogen. So let's check the mole ratio between hydrogen ratio oxygen. So the volume, the mole ratio is 2:1. The volume of hydrogen is 1.2 decimeter cube. We have gotten iron. So we can ask ourselves, what is the volume of oxygen? So we can have 1.2 decimeter cube multiplied by 1, then divided by 2. This we are going to get 0.6 decimeter cube. So we can take 0.6, then multiply by 1000. Let's see what we are going to get. We are going to get 600 centimeter cube of oxygen gas. That will be how we are going to do in that question. So in question 4, we are told when sodium peroxide was reacted with water, oxygen gas and sodium peroxide were formed. So we're asked to calculate the mass of sodium peroxide needed to produce 6.4 grams of oxygen. So first of all, we have to write the reaction between sodium peroxide and water. Sodium peroxide plus water. Water is liquid, this is solid, so we are going to get sodium hydroxide solution plus oxygen gas. So next we are supposed to balance the question. We can put 2 there, then we can put 4 there to balance the question. So let's first of all get the RFM of oxygen gas. RFM of oxygen gas will be 2 times 16, that will be 32. Then next get the number of moles of oxygen gas. So moles of oxygen gas will be equal to mass of oxygen, 6.4 divided by 32. So here we are going to get 0.2 moles. 0.2 moles of oxygen gas. Okay, so we're asked to calculate the mass of sodium peroxide. Let's check the mole ratio between sodium peroxide and also oxygen gas. So we can say sodium peroxide ratio oxygen gas. So it will be 2:1. So we have gotten the number of moles of oxygen to be 0.2. So we can ask ourselves, what is the number of moles of sodium peroxide? So we can say 2 times 0.2 divided by 1. So here we can get 0.4 moles of sodium peroxide. So next, if we have gotten the moles of sodium peroxide, we have to look for the RFM of sodium peroxide. So RFM of sodium peroxide will be equal to 2 times 23 for sodium plus 16 times 2 for oxygen. This we are going to get 78. So mass of sodium peroxide will be equal to moles times RFM. So how are we going to do this? 0.4, which is the moles of sodium peroxide, multiplied by 78, which is the RFM. So here we are going to get 31.2 grams of sodium peroxide. That will be the mass for sodium peroxide in 4 bath A. So we proceed to 4 bath B. We are told what mass of sodium hydroxide was produced when 6.4 grams of oxygen was formed. Here we are going to talk about the mole ratio between sodium hydroxide and also oxygen gas. So sodium hydroxide ratio oxygen gas is 4:1. As you can see here, 4:1. So we have gotten the number of moles of oxygen gas to be 0.2. So you can see if 0.2 moles, what mole of sodium hydroxide can we get? So you can have 4 times 0.2 divided by 1. This will be 0.8 moles of sodium hydroxide. That's what we're going to get. So if we have that, we can get the RFM of sodium hydroxide. RFM of sodium hydroxide will be 22 for sodium, 16 for oxygen, 1 for hydrogen. Here we are going to get 40. So mass of sodium hydroxide will be equal to moles times RFM. So the moles of sodium hydroxide, which is 0.8, multiplied by 40, which is the RFM of sodium hydroxide. What are we going to get? So we are going to get 32 grams, very easy, of sodium hydroxide. So we proceed to question number 5. We are told magnesium carbonate decomposes when heated according to the question, when heated. So here we have magnesium carbonate being heated, then we are going to get magnesium oxide and carbon dioxide. So we're asked to calculate the volume of carbon dioxide measured at STB, that's standard temperature pressure, produced when 8.4 grams of the carbonate is decomposed. So first of all, we have to look RFM of magnesium carbonate. The RM of magnesium is 24 plus the RM of carbonate is 12 plus 16 times 3 for oxygen. What are we going to get? We are going to get 84. So next we get moles of magnesium carbonate. Moles is equal to mass, which is 8.4, divided by RFM, which is 84. Here we are going to get 0.1 moles of magnesium carbonate. So let's see now the ratio between magnesium carbonate ratio carbon peroxide. It is 1:1. So if we have 0.01 mole, what's the moles of carbon peroxide? It will be the same. So we are going to say 0.1 multiplied by 1 divided by 1. So we are going to get 0.1 moles of carbon peroxide. So let's proceed. So if we have gotten the number of moles of carbon peroxide, what have they asked us? We are told calculate the volume of carbon peroxide measured at STB. So we have the moles of carbon peroxide. We can say 1 mole. 1 mole of carbon peroxide can have the volume of STB, which is 22.4 decimeter cube. So we can ask ourselves, what about 0.1 mole of carbon peroxide? Moles of carbon peroxide, what can it give to us? So we can have 0.1 multiplied by 22.4 divided by 1. Here we are going to get 2.24 decimeter cube of carbon peroxide. So we can have this 2.24 decimeter cube multiplied by 1000 to convert the volume of carbon peroxide in centimeter cube. We are going to get 2240 centimeter cube of carbon peroxide gas. That will be how we are going to do for that question number 5. So next we are going to go to question number 6, which is an extended question. Try to answer it and share your answer or respond on the comment section. Thank you. That is the last part for the chemistry of the mole. So in the next class we are going to start chapter 3 form 3. That's the organic chemistry 1. Thank you.